and let me record.
Recording in progress. So yeah, today I put some slides together about what's been going on recently in neural music synthesis. It's just sort of something that I find really interesting and something that I think could yield some really interesting tools for producers in the future. So the lay of the land generally right now is that generative models have been getting really, really good for things like audio, or not for things like text and images. So here's a sample of faces. Oh, it's covered up by, nice.
Can you move that?
Can I? Okay, hide it. Hide video panel. That's not what I want at all.
I didn't use it all over faces.
Hell yeah. Sure, why not? Okay. So yeah, these are some, this is a selection of faces that have been generated by StyleGAN. And as you can see, they've achieved some very realistic looking results. Similarly, things like GPT-3 have been able to generate very realistic and human looking pieces of text. However, audio is, oh, this GIF doesn't play, I'm so sad. Audio is very difficult because it carries information on probably one of the widest ranges of time steps that is available in data. There is important semantic information about audio pretty much throughout the entire clip, which would be however long the file itself is, and also down to probably 1/1600th of a second, or 1/16,000th of a second, which is typically what raw audio will run at in terms of sample rate. So yeah, this presents a very interesting challenge for,
what is this GIF supposed to be? Is this like
it's,
generated audio?
we can exit out where it still won't play. That's funny.
I think GIFs on like Google Slides are weird because I think if you just try and copy paste it without doing like the file insert.
I did file insert on it.
Oh,
And it
really?
still
It still
doesn't.
did? That's
Oh
horrible.
God.
Sorry.
Oh wait, we can. This is why I have this here. Can go to the WaveNet. Here we go. So it's just a nice little zoom through these very wide varying time steps on many orders of magnitude. So continuing on from this. Yeah, so here's an example of this where specifically in the arena of guided voice synthesis, you'll often find a trade-off between temporal stability in small time steps and large time steps, where, let's see if this, can we get this to work?
Some years ago, never mind how long precisely, having little or no money in my purse, and nothing particular to interest me on shore. I thought I would sail about a little.
Yeah, so this is it's very stable on the long term. However, in the short term, it doesn't necessarily cohere with itself as well as one would expect, say, a human talking to
What is
someone.
coherency here? Like, is it like kind of like intonation between different words?
Yeah, essentially how well the words connect. So, and here is the same thing done by a different model.
That's SpongeBob.
It is SpongeBob.
Wait, did it switch to like Porky Pig?
So that's the point, right? So on longer, when you give it these longer passages to say, right, because there's so much information that it's trying to cover in the short term, over the long term, the goal tends to lose track of the goal a little bit.
Okay.
Yeah.
That
So
was Porky Pig near the end, right?
no, that's just SpongeBob still, but it was
SpongeBob?
it had such a hard time getting from the text to the audio that it just sort of lost all the words. And yeah, so you can see in that one, the intonation is a little bit more human, like, and the words will flow together a little bit better, but there is that trade-off.
Why can't you just chunk it up?
Well, chunking it up will obviously make it so that you can't really have great coherence between the different chunks.
So yeah, you're just basically trading off like
Mhm.
manually created breaks for other visuals, which like for sentences, it
Right.
seems like that.
For sentences, it can work.
But
Yeah,
then it's like,
but still, like as we're getting to the issue of music, then we see where that can also become a problem. Where so music essentially takes that problem and makes it just a little bit more complicated because there are so many different sort of time steps on which music will carry meaning. So obviously there's the timbral, like what does this instrument sound like? And then that's sort of the smallest time scale. Then on a slightly larger time scale, there's what are the actual tones that are being played by the instrument? And do they make sense in context with each other? And do they make sense in a rhythm? And then what's been probably the most difficult to cover if you like for all the recent work in the field is how do you manage to create, an intro, a chorus, and something that will be referred back to? Because this is, even though they're apparent in the data sets they're being trained on, it still is really hard to cover just that wide of a gap in time steps when it comes to being able to recreate the sequential information. So one of the the first of sort of the very modern approaches to generating audio information was sample RNN. Sample RNN, it takes a very and sort of intuitive task when it comes to modeling a function, which is just a density function of the probability of a sample given all previous samples.
Sure.
A sample being sort of what position the wave is at any given step in time. And then all this stuff is just saying that it's using some pretty traditional sort of components of RNNs, like an LSTM unit or a gated recurrent unit, which are sort of the two things that have been in place for a while as sort of, the elementary recurrent neural network components. But what sample RNN does is it'll create sort of a hierarchy of tiers. That's what actually will mean when you're reading about this, it'll probably run into stuff called like hierarchical models. And the hierarchy is just creating different tiers that will look at different time steps independently, but still interact with each other. So here in this diagram, they have 3 different tiers, and each of them is dilated by a factor of 4. So here you can see the bottom tier is getting each individual sample. Then the next one up is getting batches of 4 samples, and then sort of feeding them down into the result of the net.
so
Bottom
in
line.
tier 2, it's not like looking at the data
Mhm.
again at each tier. It's just it's hierarchical. So it's like it's only looking the base
Yeah.
layer is the one that's looking at the actual raw data.
Yeah, so actually, I'm not entirely sure on that because I think that might be actually because I think the one I was reading, I'm not sure whether this is the one that has all of the data feeding into all the layers, because I
Sure.
think that is something that actually happens.
I would be
In some
surprised,
models,
like,
because
there are a lot of models. Like
I assume that based on this diagram, it's just that you have sort of sample 1 to 15, then sample 16 to 31 going into the top layer. And then those same samples will also be feeding into tier 2, as well as the results from tier 3. And they all sort of cascade forward down into tier 1, which is where you get the prediction.
Okay.
And sample RNN is the model that is used most by a group called DataBots, which is probably the most well-known group that's currently working with like generated AI music. They do a lot of stuff using sample RNN that trained on very specifically stylistically distinct and rhythmically angular genres of music, just because I think that it's definitely a little bit easier when we're not super restricted down into generating something that has very distinct rhythmic characteristics. So here is,
Before you play that, so just so I understand right, sample RNN, because it's recurrent, can take in arbitrary time steps. or like arbitrary lengths of input.
Yes. So here is Outer Helios, which is 24/7 free jazz live stream from sample art using sample RNN from DataBots. So it's very amorphous in terms of rhythm, which is, as we saw, like sort of, it's simultaneously a feature and a bug of the model.
You like jazz?
Yes. Yeah, so they had this running. They had this running 24/7. This is like 10 hours of music. It's because this is an archive video.
Yeah, so it's just a bot that's just running directly. That's so interesting. Okay.
Yeah. So
I don't know that I would listen to that afterwards.
come on. So Google's WaveNet actually takes a very similar approach in that it has sort of a hierarchical set of layers, which with upper ones, with different ones being more or less dilated in time. And here they have a little diagram where they show that, well, something important about this one is that the dilation steps between the layers are actually different. Like they vary between layers, which will probably give it a little bit more variation when you try to train it.
In this case, is it saying that the output is the next step's input, or is that just sort of like
Yep.
confusing animation?
Mhm. Well, the output is essentially the output is the next predicted sample. And
Yeah.
that sample is being fed forward and then used to predict the next one. So WaveNet hasn't been used, from what I've seen, much in terms of, completely unrestrained generation of music, but they did, like, it's more being used by Google as like their voice synthesis. But in the original paper, they did feed it some solo classical piano, which actually sounds quite good. And then this is another sample. Yeah, so it's sort of a common theme with AI generated music is that it can be very detailed granularly, but as sort of has been the theme, it's tends to fall apart over larger time steps and in recognizing sort of the bigger patterns in a song. But one of the more recent and interesting applications that they used WaveNet for was NSynth. They essentially used WaveNet to learn embeddings of different instruments in their timbres, where they were trying to predict essentially the probability of audio given a certain note for a certain instrument. And then from there, they were able to actually create embeddings for different instruments, which is interesting. And that eventually resulted in NSynth, which I think is open source, and you can use it to sort of combine different instruments, which is really cool. Yeah, here are some of the embeddings that they ended up learning from the pipeline from the original sound into an embedding, and then using that to get back out of the space and reconstructing it into something like the original sound.
It's really interesting when you compare the two. Like, it seems like it fills in a lot of information beyond what is in the original partials.
Yeah, I think that that's just sort of a matter of, embedding into a lower space and getting it back out. There will always be some kind of artifacting.
Yeah. That's super cool.
Mm-hmm.
The fidelity is quite good.
Yeah.
But it's interesting that in that sound, it's more information.
Mm-hmm.
Are you able to tell if fidelity is good just looking at the picture?
But yeah, that's because that's a different model from the other one.
Oh, it's different. Okay.
But that's essentially an extension of that original model that's being used for a different application. But yeah, this is the wildest model of the three that are sort of currently being used. It's the one that OpenAI employed for Jukebox. And they sort of take a slightly different approach to sort of making the task of making audio more sort of digestible for a model, where instead of explicitly taking just longer time steps, they use like multiple layers of CNNs that get progressively coarser in terms of detail, and then they essentially compress the audio down, and then use they use transformers to upscale it back up to something that might sound like the original audio. This is very difficult to understand, so I'm going to tab over to the Jukebox blogs that it might be easier.
Or is it transformers?
It uses CNNs and transformers,
Okay.
but okay, so CNNs, I think I might have misspoke. So it uses a transformer to generate new audio in the compressed form. Then it uses those, I think, original CNNs to upsample it. So yeah, this is, so for example, for the original audio like this, it will progressively compress it more and more. But using CNNs such that it doesn't necessarily lose quality as much as it doesn't lose sort of the semantic values of the audio as much as it loses it basically tries to reduce the loss of semantic qualities as much as it possibly can using CNNs to compress instead of other more traditional methods.
Can you notice how affecting it?
As you get to like the top level, you can, because eventually. Mhm. Yeah. But essentially what it's doing then is it will then use a transformer to go from, I think it takes in a bunch of information, but a lot of it's been using lyrics as well as like genre information and tagging. And then what it'll do is it'll use a transformer to go to this top layer and then use, and then upsample it back up to the original quality, which is the hope. So I believe it is using transformers, and that it uses transformers to get up to this layer, then uses a CNN to decode back to the original audio. So this is completely generated by the model. And you can see that.
Is it speaking? Wait, can you play that again? Sorry.
Yeah. It's actually very cool.
Yeah, it's gibberish, but it's like my brain is like, oh, I should be able to understand this. It's speaking English, but he's very much not.
It's got really good artistic
Wait,
merit.
sorry. Well, can you go back to that?
Yeah.
Okay, so when it generates novel compressed audio.
Yeah. That's from a transformer from lyrics to the compressed audio.
So how is it sharing an embedding space with the previous compression?
So yeah,
Like, where is the generation coming from, I guess?
so the generation is generating this. It's generating compressed audio. I think that's really the purpose of them compressing it so hard, is such that there's little enough information needed. I think it's I'm pretty sure that it is, because it's using a transformer to go from text to this audio. So yeah, I'm pretty sure that that's what's going on.
So it's similar to broadly, like image stuff
Mhm.
that takes in a bunch and then navigate the embedding space.
I'm not entirely sure.
I think that's correct.
Yeah, I'm pretty sure. But yeah, So yeah, basically the general purpose of all the compression is to get it into a small enough space such that you don't need to handle every single detail, and then you can upsample it back up using their model, and then get it back to that kind of audio. And then what people have been mostly using Jukebox for is to make continuations of songs. And this is Basket Case, but it's been continued by Jukebox multiple times. So they're passing him the lyrics, so it still knows what to say, but it's well, it's trying its best, and it's obviously there's so much other information to carry that it's very difficult. And it breaks down into math rock essentially. Yeah, but then as it continues on, it will get more and more arrhythmic. This one is actually very interesting because it completely changes the rhythm. And it completely changes the tempo.
So is this, has it seen the other Green Day? Or
I assume this has been trained on a couple of Green Day albums. Either that or I don't think they train on like a huge data set. I don't think it's like that.
I feel like it kind of
It's got a really good grasp. It's really wild because it's doing really well as a thing.
I feel like this is like if an alien picked up on some radio waves. Like, yeah.
We can do this. Cool chord change there.
I think this is like metal sounding.
Mhm.
All right. I think
That's it.
we get the idea.
I think that's about all I had time to make slides for. So good. We got to 1:33 p.m.
Cool. No, this one's really cool. Thank you for listening. There's us.
There's us.
Yeah, this is super neat. I don't know that I have any questions. I didn't expect it really well, but yeah, do you have anything?
I was still like comparing it to images. It's just because like so images you get a smaller amount of data, manageable amount of data, you resize the images. Compression is similar, but it's interesting.
Yeah, because I think that the point of the compression is that I think that traditional methods of compression are probably not great. They're not great in terms of adding noise versus preserving semantics. So I think that trying to do it using like convolutional networks is probably
It's like smarter
making
about-
the embedding a little bit cleaner.
It's like throwing away. It's smarter about what information is thrown away.
Yeah, which like you can do some of that for images too, and I think probably people do.
Yeah, there was a bunch of like that's what variational autoencoders are basically, where like you kind of have this like hourglass structure, where you put in an image and then like it like sequentially compresses it down into like a small embedding, and that embedding acts as a compressed representation, which can then be restructured by the other side of the hourglass. And so what it's doing is it's basically storing like the information isn't. I mean, some of the information is lost, but what you're trying to do is basically store information that appears frequently in the image in the weights of the model. So like, imagine that all of your pictures are like of the blue sky, right? You don't need to encode blue in your underlying embedding space. Blue, then you can just store the blueness in the decoder and the encoder and decoders. And it will know that like, okay, I don't need to care about, like, I don't need to keep track of what color the sky is because it's always blue. And so on, when it decodes the embedding, it'll always put blue sky. This sort of be like, that's how I intuit.
I think it also like because it keeps like it keeps like a dictionary of specific specific values that it's going to be compressing to.
What, the exit?
No, the this one, the VQVAE.
Oh,
Well, like it keeps track of like how much they're being used and like shuffles them around in certain ways, depending on like whether one is not being used that much.
Yeah, that makes sense. That's really interesting. That's cool. All right, thank you. I think next week, we're gonna be doing we're doing this weekly instead of bi-weekly because we have interns. I think next week we have Alex presenting on something. The week after that, I don't know what he's gonna be presenting on. And then the week after that, we have Sarah presenting, although we might switch to